Hi everyone, Mrs. Basega here, and today we're doing the review packet for Unit 10. Now, with the year being a little funny and us testing before break, some of the things on this packet you actually don't need to know. So when it talks about anything having to do with refraction, like this index of refraction equation, or this mention of index of refraction, feel free to skip that. And one of the classes has a review packet that has a few extra things. Focus on all the questions that I'm going to review because those are the ones on this year's test. All right, so right off the bat, let's talk about the speed of light. The speed of light is the same for all colors of light. So whether it's red or green or blue or ultraviolet or infrared, the speed of light is the same value for all different colors of light. And since it's the same speed for all, then it should take the same amount of time to travel to and from the moon, no matter what color it is. So one more time, even though gamma has more energy than blue, for instance, that would take the same amount of time because the speed is the same. Now, in this unit, we know the speed is the 3 times 10 to the 8th meters per second. So we want to do speed is distance over time. Put in 3 times 10 to the 8th meters per second for the speed. We're trying to calculate the distance, and the time is 2.51 seconds total. This gets us a distance of 753, and then 3 and 6 zeros. Lots of zeros. But I want to point out that's not actually the distance from the Earth to the moon. It's this far total. When the light travels for 2.51 seconds, it's traveling from the surface of the Earth to the surface of the moon and back. So if it's this number total, then the distance from the Earth to the moon would be half of that. So half of that would be 376,500,000 meters from the surface of the Earth to the surface of the moon. Right? Cool. So all the parts of the electromagnetic spectrum. We always need to know these in order from low energy to high energy. And the low energy is the long wavelength side. So that's our radio waves, microwaves, infrared. And I remember infrared is here because infrared is below red. All right? On the other side of the visible spectrum is ultraviolet because it's above violet. X-rays and then gamma are the shortest wavelength, highest frequency, high energy. Gammas are the most dangerous. They actually consider this one of the 3 types of nuclear radiation is gamma. So the low frequency end of the spectrum is the radio waves. The highest energy, let's go to this side, that is the gamma rays. And they all travel at the same speed. So when I'm trying to find wavelength or calculate wavelength, I can always put in the 3 times 10 to the 8th meters per second in a vacuum. With the one caveat being I need to change this to regular hertz instead of megahertz. So take out that little sheet with the conversion factors. I'm going to replace the capital M for mega with 10 to the positive 6th. This is actually 92.5 million hertz. So I need to put it in base units before I can do this equation. This gives me a wavelength of 3 and change meters. So dividing by 92.5 million on both sides, I only get about 3 meters of distance. Radio waves have really big wavelengths compared to gamma rays, which are the size of atoms. So a portion of light in the ultraviolet spectrum has a wavelength of 125 nanometers. So I'm going to actually just have you do the same equation again. So you get a point for the equation, a point for the substitution, put in that speed of light is 3 times 10 to the 8th. We have 125 nanometers, and we're solving for frequency. Right, so these are just, one is finding wavelength, one is finding frequency, but the speeds stay the same. And nanometers, so pull out the little tiny conversion sheet, that's 10 to the negative 9th meters. I would strongly suggest to do this in Desmos. And the reason is, in Desmos, when you do your dividing, you can make sure that you're dividing with the right order of operations. Now, everything in the denominator is going to be divided. Whereas if you do this on a graphing calculator or like just the regular app on your phone, it might think you're multiplying by 10 to the negative 9th when you're dividing by the 10 to the negative 9th. And just to check, your frequencies should come out very big. Very, very big. You should be coming out with frequencies that are like, 10 to the 15th for ultraviolet light, 10 to the 14th for visible light, and even radio, which is the lowest spectrum, part of the spectrum, even radio waves are like in the millions of hertz range. And again, they all travel the same speed of light in a vacuum. So we know light is a wave because light does wavy things. And one of the wavy things light does is reflection. You can see the color of this paper, of my hands, of this board. You can see that because it's a rough surface. It's called diffuse reflection. Diffuse reflection would be, reflection off a rough surface in which it doesn't form an image because the rays scatter randomly, right? So a good example of this type of reflection would be this red stand or this black desk. If you look at it and you don't see your own image in it, it's diffuse. The other check is if you look at it and you see a color, it's brown, that's diffuse. Whereas specular, this is off a nice smooth surface. So think specular, S for specular, S for smooth. Specular reflection is off a nice smooth surface, and that makes the rays all kind of stay aligned. So I'm going to do the same example I did in class, but let's say I am looking at a person and their head's over here, and then their torso and their legs. Because the rays stay in order, this person's head would show up over here, their torso would show up over here, their feet would show up over here, and the image would stay in order. Specular reflection is when the rays stay in order to form an image. So an example of this might be the reflection off a shiny car, the reflection off a mirror, the reflection off a smooth lake, right? If you can look and see an image of yourself, that counts. Now, you are going to have to draw a reflection ray diagram. These diagrams have 5 parts. It has an incident ray, where the ray of light is coming in, a reflected ray, a normal line, that's the line perpendicular to the surface, but this person labeled the wrong angles. The angles should be from the incident ray to the normal line, or the reflected ray to the normal line. So let's draw a corrected one on this side. So as the light ray comes in, our I for incident ray, the normal line is formed as the perpendicular line that crosses the mirror at this point. So normal, think 90 degrees. This is the line from which you measure the incident ray. And we call that theta I for the angle between the incident ray to normal. The law of reflection says that this angle, the incident angle, must be equal to the reflected angle. So if you're not great at drawing, maybe you put the little hash marks here to show that these are meant to be equal. We put the R for reflected ray, and that would be my correction. The incorrect thing was they labeled the wrong angle. So we drew the corrected diagram with all the labeled parts. And if this is 38 degrees, then what should this angle be? Yeah, it should be 52 because it's got to add up to 90. So 52 for the incident angle, 52 for the reflected angle. And just in case, because this is a geometry concept, not a physics concept, it's because the 52 degrees and 38 degrees add up to 90 degrees. These are complementary angles. Okay, when you look in the mirror, you see an image that's the same size and opposite orientation to the object. And if you don't believe me, like, look at yourself in the mirror and hold up your right and left hands. When you look at your right hand in the mirror, it actually shows left hand symmetry, right? In a mirror, your orientation is 180 degrees off from what it normally is. It's like a flip. You might remember this from when we did this in class with the image versus the object, where you had an image of, I think, Pusheen, like a cat on one side, and then a cat on the other side. And the orientation was flipped from what it normally is. All right, so more proof that light is a wave. Light is a wave because it does diffraction and interference as well as reflection. So this example is an example of diffraction. The wave is going around a small object or through a tiny hole. And if you have trouble picturing like why this would be like the double slit experiment, imagine I have my diffraction grating where it has the little holes. D would be the distance between these little holes, but D would also be the distance, like the size of this wire. So to determine the distance of the wire, the thickness of the wire D, I'm going to use the one equation, the only one equation that gets used for diffraction and interference. We have Y is equal to 3 centimeters. Unless I say otherwise, M is 1. The wavelength of red light is 640 nanometers. And L is 0.5. So we have everything we need except for D. Notice one thing though. You need to turn everything to meters. I know we've done 2 conversion factors before. Let's do 2 more. Take out that little sheet that's got like the conversion factors. 3 centimeters is 3 times 10 to the negative 2 meters. 640 nanometers is 640 times 10 to the negative 9th meters. So when I put this into my calculator, I would strongly suggest using like a Desmos as opposed to like a calculator, like a graphing calculator, because when you do this division, you're dividing by the 3 times 10 to the negative 2 on both sides. In a regular calculator, if you forget these parentheses, you're going to come up with a number that's the wrong power of 10. If you do this in Desmos, however, it automatically puts things in the denominator for you, so you don't have to worry about getting your powers of 10 like divided instead of multiplied. Remember to put parentheses in the denominator if you're using any other calculator but Desmos. As a check, D should be a very small number. This would be 4 zeros. So I would actually write this as 1.06 times 10 to the negative 1, 2, 3, 4, 5 meters. Your value for D should be a very small number. When we did this in the lab, these were so small that you couldn't see the little tiny openings. So D should be a small number. Now, the next few are all proportions. They're all based on this equation. So it's asking about the distance between the two dots. So do you remember, like, we shine the laser at the diffraction grating and it makes a series of dots. If you used a green laser instead, it's the same equation, except it's changing the wavelength. You need to know that green wavelength is smaller than red because G is on the higher end of the spectrum than R in Roy G. Biv. So green is a smaller wavelength. If green is a smaller wavelength, then Y is going to be smaller too because it's a direct relationship. So I would say that the dots are getting closer together because Y is getting smaller because wavelength got smaller. Now for C, I'm not a super big fan of how this wording turned out because I'm still asking a proportions problem. But I asked if the thickness of an even thinner wire was measured. So I'm indicating that D is getting thinner or smaller. If D gets smaller, I think the wording was just funny because it says thickness here and then thinner here. So the wording is supposed to indicate that D is getting smaller. If D gets smaller, I'm dividing by a smaller number. So Y should get bigger. That nice inverse relationship is indicating that Y is getting bigger. And if Y is getting bigger, the dots are going to be farther apart. Last one in this pattern. It asks if the screen is moved closer to the wire. That's L. If L goes down, then Y goes down. This is a direct relationship. And you can imagine if I moved the screen from here to here. If I moved the screen here, then the distance between the two dots would only be this big instead of this big. So this proves that light is a wave because it does diffraction when it hits the wire. It goes around a small object or through a small opening. And it does interference. The bright spots are constructive interference. The dark spots are destructive interference. So all in all, this actually shows light as a wave in two ways. It does both diffraction and interference. Okay, so on to photoelectric effect. I know it's not on here, but in case you missed it, photoelectric effect is showing that light is a particle. And you can remember this like P for photoelectric effect, P for particle. Now, why is it a particle? When light is behaving like a particle, then it does not do all the other wave behaviors. It doesn't diffract, it doesn't interfere, and because it doesn't interfere, if you have a light whose frequency is too low, you can't just like add them together to make electrons come out. They don't interfere with each other in this experiment. So it's really funny because in so many times, light behaves like a wave, but in this instance, light does not interfere. It collides one-on-one with particles to eject electrons from a metal. So if you're having trouble picturing this, electrons are being emitted from a metallic surface when light strikes the surface. So light is coming in, electrons are going out. Light is the photo, electrons are the electric. So when we do this graph, you see that there's like a cutoff, a frequency below which no electrons come out. Okay, and we're going to use what we have to make a best fit line. So there's a cutoff frequency, a frequency below which no electrons come out. Basically, if the light doesn't have enough energy, they don't interfere with each other, and therefore no electrons come out until the light has enough energy, enough frequency to work. So the cutoff frequency, in mine, it's right between 4 and 5. So let's call this 4.5 times 10 to the negative 15th, 10 to the positive 14th, there we go, hertz. So I'm going based right here, 4.5, 10 to the 14th. Sorry, my writing's so bad. Okay, next, the work function. I'm actually going to use that data point right at the cutoff frequency. Feel free to use any other data point if you want, but the reason I'm using this one is that we know the energy of the light is equal to the work function plus kinetic energy. So I'm purposely picking a data point whose kinetic energy is 0. At this point, the frequency of the light is related to the cutoff frequency. The frequency of the light, the 4.5 times 10 to the 14th, we can get that light's energy. So I'm going to do H times F. So that's 4.14 times 10 to the negative 15th times this frequency of light, which I didn't give myself enough space for. And I see the minimum required energy for electrons to come out is 1.863 electron volts. So again, what I did, because it wasn't really clear in my writing, I took H, Planck's constant, times the frequency I just got, at which the kinetic energy is 0. And then I see that 1.8 is equal to the work constant plus 0. So this must just be the work constant. Right? And you can totally do that with a different data point. Like you could put in the 5 times 10 to the 14th here and use its kinetic energy of 0.1. It'll give you the same answer. If yours is a little off from mine, no worries, because remember, I'm basing it based on the best fit line of this graph. And if you estimate it a little differently, that's fine. So now, light is coming in, it's hitting a surface. If its frequency is only 3 times 10 to the 14th, that is below the cutoff frequency. And so no electrons come out. No electrons are emitted. If there's not enough energy, the photoelectric effect doesn't happen because my light waves are not constructively interfering, so they're not adding their energies and they're not escaping. So I said no. Electrons are not coming out because 3 is less than 4.5. But if something has a frequency of 10 to the positive, 10 times 10 to the positive 14, that's out here. Yes, that is definitely making electrons. This is a lot of energy. So if a lot of energy goes in, it makes faster electrons. And that makes sense to me because if more energy in, more kinetic energy out. So I want to show you the easy way and hard way to do this. The easy way, you have a graph. The kinetic energy is right there on that graph. It is something between 1.5 and 2 electron volts. So if you said like 2.75, because I read it from the graph, that works. If you want to calculate it because it says the word calculate, then what you would do is we want the energy of the light. So we're going to need that in a second. We have my work function. I've calculated it earlier, and I'm solving for KE. You do kind of have to do this initial step, though. This 10 to the 14th is not the energy. The energy is Planck's constant times that frequency. So I would find the energy of the light, then subtract the work function, and be left with KE. So the energy of this light would be 4.14 times 10 to the negative 15th times 10 to the positive 14th. And believe it or not, I can actually do this in my head because all the powers of 10 cancel. So I have 4.4 electron volts. That's my energy of my light, lots of energy. More energy than violet light, so ultraviolet. So this is my energy of my light. It takes 1.863 electron volts to get it out of the atom. And so how much kinetic energy is left over? We're just going to subtract.
Oh, the quick correction. Because this is 4.14 times 10 to the negative 15, this should be 4.14 times, and then these powers of 10 cancel. So if the energy of light is 4.14 electron volts minus the 1.863 work function, then the remainder of the energy is this 2.27 electron volts.
So light for a given frequency falls on a metal surface, and it causes electrons to be ejected from that surface. What would happen if the frequency of light were doubled? We actually have this on our chart, guys. So if the frequency doubles from 5 to 10, it definitely increases, and it increases big time. It doesn't just double the energy output, because it goes from 0.1 to like 2.5, like way up here, right? So if I double the frequency, it does double the energy of light, but it actually more than doubles the energy of the electron. So I said B. And I do want to point out like a little bit of a typo here. These choices should read electron because it is electrons being emitted in photoelectric effect. The light comes in and electrons come out. So one electron would be emitted, but with much greater kinetic energy. Now the kinetic energy is like 2.5 instead of 0.01 or 0.1. So finally, let's talk about where light comes from. Light comes from either a very hot object emitting light proportional to its color. Hotter objects have higher energy colors like blue, right? Or if you have an atom where the electrons are becoming more stable. So it asks, which of the following photon energies would not be found? Well, it can go from 6 to 5. So this one would have an energy of 1. It could go from 5 to 3. So this one would have an energy of 2. It could keep falling, and it could go from 3 to the ground. It could have 3. So assume all the energies. It says it starts in the n equals 4 state. Here's all the potential pairs. It could go from 6 electron volts to 3, so this would be 3 again. It could go from this one all the way to the ground. So if we're going from 5 to 0, that's 5. If you're like, wait, why doesn't it just be like 1, 1, 1, 1? Well, that's because these are the labels. So this side is just labeling the energy level. This left side, these are the actual energies. So if you're like, wait, I got all my energies to be 1, you're looking at the wrong side. And notice all of them are on the list except 4. I've got 1, 2, 3, 5, but 4 there was no combination of jumps that go down to get 4. The one with the longest wavelength is going to be the one with the lowest frequency, lowest energy. So what's the one with the lowest energy in this picture? Was from n equals 4 to n equals 3. That's actually in the infrared part of the spectrum, it's so low. And number 10 actually wants you to do a very similar thing. I think the wording was just a little confusing. So it says, draw the arrows to show all the energy jumps that emit a photon. So just like I did before, arrows going down. So emitting a photon would be these 3 options. Then it says, label each jump with the energy change associated with the jump. All right, from 2.6 to 0, that would be 2.6. I'm subtracting these in my head. From 2.6 to 1.5, this one would be 1.4. From 1.5 to ground would be 1.5. It says list the letter of the jump below. You can skip that if you want. I think in my head I might call them like A, B, C or whatnot. But A's energy would be going from 2.6 to 0 to give me 2.6 electron volts. Right? B's energy would be going from 2.6 to 1.5 to get me. Oh, wow, math in my head is so great. This is a 1.1. We're very good at this. You would have caught this. All right, and then C was going from 1.5 to the ground for 1.5. There we go. So the lowest energy jump was B. The frequency of this photon. So I know its energy is 1.1. I know H is 4.14 times 10 to the negative 15th. And so I'm solving for F. Dividing by H is actually, it's a very small number. So you should be getting very big numbers, because if you're dividing by a small number, your frequency should be very big. If you're not using Desmos, I'm going to remind you again to put the parentheses in the denominator. If you do this in your calculator and you forget this set of parentheses, you're actually going to end up with a number that's very small instead of what I'm looking for, a number that's very, very big. So this vibrates up and down 2.65 times 10 to the 14th up and downs per second, right? So I don't know if you want to write out 265 and then start putting more than a dozen zeros over there. It's fast, very big. So to get wavelength is actually multi-step. So first let's take the highest energy jump, that was A, and take its energy. This is just like before, so I'm going to speed right through it. We're dividing by H on both sides. And a double check, frequency should be a very big number. A bonus nice thing about Desmos is if you have to do the same calculation more than once, you can just replace part of the calculation and not have to retype. So 6.28 times 10 to the 14th. So I needed to get frequency first so that I could come back here to get wavelength. Right, this is a light, so it travels at the speed of light. So we're gonna need to divide by this big old frequency, dividing by that number on both sides to get our wavelength. A check should be the wavelengths of light should be very small. This is 4.77 times 10 to the negative 7th meters. If just for funsies, you want to put this in nanometers so that it looks comparable to what we're used to, we would go here. This is right around like the blue part of the spectrum. If violet is like 410 nanometers, then blue is at like 477. Number 10, the gases present in the star we'll be able to tell because the lines should match up. So when we say justify your answer, you want to talk very specifically about how the bright lines from the spectrum match. So in the star, A would be there because this line is here. This double bar is here. And this line is here. Now there's only two other features left in the star. I see a single bar here. That matches up with D. That's a good contender. And a double bar here. That matches up. That's a good contender. So I'm going to very specifically say A and D are present because the bright line spectra match. Elements have unique bright line spectra. It's because they have specific energy levels having to do with their internal structure. The bright line spectra of the gas matches the bright line spectra of the star. It's how we know stars are made of hydrogen and helium primarily. Now, in this picture, it has light shifted towards one direction or another. I actually have to know something about our universe to answer this. And the thing we have to know is that the universe is expanding. The universe is expanding because of the Big Bang, but also because all the evidence points this way. So let's think about it in terms of the Big Bang. We have evidence of the Big Bang because of the light we see. When we look out at the solar system and the galaxy and the universe, we're not in the center. We're out like here somewhere. There's actually no center of the true universe. We think there's a center of the observable universe because you and I are the ones doing the observing. But anyways, let's say that we're here. At some point in time, we were closer to the origin. But notice that every other galaxy is going to be farther away from us than when we started. With all that leftover energy from the Big Bang, the galaxies that are far away from us are moving away from us very fast. In fact, can you see how like two adjacent galaxies might be moving away from each other, but at a slower rate than these two that are on the opposite sides of the universe from each other? Right? So we need to know that redshift goes with away. These means the stars are moving away from us. Blue shift would mean towards, but there's very little evidence of things moving towards us. There are a handful of things moving towards us, but in the overall picture of hundreds of billions of galaxies, having a handful of things, literally less than 100 things moving towards us, most of them are going away. Light shifts in this direction because as things are going away, the Doppler effect stretches out the rays of light. So if this is my standard Doppler effect picture that you've seen me draw several times, if it was moving towards us, the waves would be crunched together. The wavelength would be small, and blue is on the small wavelength side of the spectrum. Red has these waves that are stretched out. The wavelength is big, and red is on the large wavelength side of the spectrum. So some people remember this like rabbit, R-A-B-T, red away, blue towards. It's just harder simply to picture Doppler effect of light because we're so used to hearing it with sound. With sound, I can literally hear the woo. That indicates something moving towards and then away from us. But with light, it's worth it to memorize it. Red away, blue towards. And in our universe, almost everything is red shifted because almost everything is moving away from us. Right? So, in terms of the origin of the universe, when we look out at the night sky at the cosmic background radiation, when we look out at the night sky at the cosmic background radiation, I actually put this in my class notes as microwave radiation. If you remember from the electromagnetic spectrum earlier, microwave would be even longer wavelengths than red. That indicates things moving very, very fast away from us. In fact, items on the exact opposite side of the universe from us, they are moving away from us so fast that we actually see them as kind of like a glow in the microwave part of the spectrum. So what does this mean? It means things are moving apart from each other because it's not only red shifted, it's like microwave shifted, even more than red. It means the universe is expanding. You can think of this as the leftover energy from the Big Bang. Even though we can't see it with our eyes, we can measure this with telescopes and actually take pictures of the microwave background, just like we would take pictures of the sun or the moon. Leftover energy from the Big Bang. All right, guys, best of luck.